Okay, welcome back. We are still in chapter 3. One of the interesting comments I just received from a colleague of ours in this meeting was that the class is more fun because everybody tries to talk to each other and interact, and it's kind of engaging and looks a lot different, more active, more energized. So I would really recommend these type of recordings for those who are in a stressful situation or desperate to basically grab the material through the recordings. But also I would really recommend for you guys to come in and attend the class. Attendance is really the big factor in success. I would say 10% the teacher, 30% attendance, and 60% is individual work to get you to the A+ you want to. Now we are in a phase halfway through chapter 3. We talked about nodal equations. A subset of nodal equation was supernode. Supernode is not an individual technique. It's a kind of modified massage form of a nodal technique. So that was one technique we talked about. And then we are going to talk about mesh and supermesh. And again, supermesh would be just a subset of mesh technique. Let's understand what the mesh is. I'm going to go through the chapter 2 steps, and then I'm going to explain where the mesh come from, and then I'm going to give a bit of engineering understanding and make it simpler for us to write the equation, understand where the equations are coming from, and then mechanically, robotically write the equations, solve the system, and go on. Take a look at this design. You have 3 resistors and 2 voltage sources. I'm supposed to solve this system using chapter 2 techniques. In chapter 2, what I would do, I'm going to say, let's begin assigning current. I'm going to call this Ix. I'm going to call this Iy. Before I move any further, one of the questions raised was this. This is plus minus, how come the current is going this way? This is plus minus, how come the current is going this way? If you remember in chapter 1 we said the voltage sources, the only thing we can say about them is that the voltages are fixed. The currents could go anywhere. And who defines the direction of the current for the voltage source? The environment, the circuit, the topology, all the other components. The same thing is true for the current source. The current of the current source is known, but its voltage and polarity are not known. You can go and randomly assign anything you like. But when you get to the resistors, for example, if I say this is I1, if I say this is I2, and if I say, this is I3, and this is I2, as soon as I assign the currents, voltages are not mine to do. I need to actually follow the Ohm law. The Ohm law says for the resistor, if the current is entering from left to right, then it's going to be plus on this side, minus on this side, V1, top to the bottom, plus minus V3, left to right, plus minus V2, and done. How many unknowns do I have? I have 1, 2, 3, 4, 5, 6, 7, 8. I expect to have 8 equations, 8 unknown. The rule in chapter 2 was to write component law. Component laws, and obviously you have 3 resistors. It's going to be V1 is equal to R1, I1. You can actually write these equations relatively fast because you have followed the Ohm law already. The indexes also, hopefully they match. So basically it's very easy to write these 3 equations almost blindfolded. Now we need to write the topology law. This is topology law, and it has 2 segments. It has a segment of KCl law, and it has a segment of KVL law. For KCl law, we attack the nodes. We need to know where the nodes are and basically write the KCl law for that. So, where are my nodes? Node 1, node 2, chapter 2. We are in chapter 2 now. Node 3 and node 4. This is all one node. I'm going to assume that this is going to be a reference node. And as soon as I say this is a reference node, I don't have to write the KCl law for that. I have A, B, C. Let's call them. This is A, this is B, this is C. Let's write the 3 KCl law. On node A, chapter 2, Ix is entering minus Ix. I1 is leaving plus I1 as equal to 0. Node B, I1 is entering, I2 and I3 are leaving, so it's minus I1 plus I2 plus I3 as equal to 0. This was node A, this is going to be node B. Finally, on node C, I2 is entering and Iy is leaving. This is going to be node C. Then comes the time to write the KVL law. The KVL law, you need to identify the basic loops. For basic loop, what we said, and actually there is a mathematical definition for it, we don't want to go into details, but what we mean by basic loop is that there is no other loop in it. This is only one loop. It's kind of basic building blocks of my structure. So this is my loops. So let's go. For the comfort of the analysis, I'm going to assign clockwise direction. That's going to be D1 and D2. I'm going to start from one point. If I hit a minus sign, minus polarity first, it's going to be minus. If I hit a plus polarity first, I'm going to have it plus. In this case, I have minus V1 for loop number 1, because I see minus first. Then I get to R1 or V1, I see plus V1. I need to actually modify this a bit because I don't want to create confusion. I'm going to call this Vx and I'm going to call this Vy, because I don't want this Vx and this V1 to be confused. The book has followed that, but let's just go a bit off the chart to make sure confusions are taken care of. Now I'm going to have clockwise direction. I see a minus sign, I see a plus sign, I see a plus sign. Minus Vx plus V1 plus V3 as equal to 0. This is going to be loop number 1. Let's go for loop number 2. Let's begin, for example, from this node. Again, this minus plus belongs to the component, so you can see this is plus minus. The arrow comes in, hits the minus sign first, so it's going to be minus V3 plus V2 plus Vy as equal to 0. This is going to be node D2. I'm sorry, loop D2. Now you said 8 unknowns, 8 equations, 3, 5, 3 and 3, 6, 6 and 2, 8. I have 8 equations, 8 unknown. What did we do in nodal approach? In nodal approach, we said that through a transformation of the component voltage versus the node voltage, you would take care of the KVL law. In nodal, we took care of this and we inserted all that. We found I1, V1, R1, I2, V2, R2, I3, V3, I3. We put them in and we came to a conclusion that an 8 by 8 system can be simplified only on the basis of KCl law. Similar mentality can apply. The way we are going to say is this. Through a special transformation, we are going to actually take care of the KCl law now. I'm going to talk about that transformation in a moment. Then I'm going to take care of this, and I'm going to put them inside this equation, and I'm going to collapse the system. Instead of having 8 by 8, as you can see, it's going to be 2 by 2 KVL equations applied. Let's first simplify this, and then I'm going to talk about the transformations of variables. Let's pick up the V1, V2, V3, and apply this inside this and see what happens. It's minus Vx plus V1, R1, I1, V3, R3, I3 as equal to 0. Minus V3, V2 is R2, I2, and Vy, I have the value already. So I need to replace V3 as well, my mistake. Let's replace the V3. V3 is going to be R3, I3. Vx and Vy are known, R1, R2, R3 are known, I1, I2, I3 are not known, and I need to find them. I want you to look at a tunnel. Let me actually erase this part. Take a look at this tunnel. This tunnel is actually connecting the Rogers building, Rogers Communications building, to KHE building. This is the Church Street. Tunnel is on top of the street. Now imagine the flow of people inside this tunnel. Now at some point in the morning, people who are associated with Faculty of Engineering have a class in KHE. They come in from George Valley, which is inside. Let me actually raise this. I want you to feel this because that's going to be very easy to actually follow this. This is George Valley building, engineering building. Okay? And this is for example, image art building. Okay? So it's 8 a.m. in the morning. Engineering people, Faculty of Engineering students, go through the Rogers and actually move to the class that they have at 8 a.m. in KHE. The movement is going to be this way. There are people who have a class in Rogers building. So what they do, they go through KHE and it's very rainy and it's snowy and they want to utilize the tunnel. So basically they go in and then they move this way. This is my component. This is the resistor we talked about, and we have characterized this resistor before. The size of the tunnel, the friction of the tunnel, everything else came in to identify the component for us. For this component, there are people who are going this way. For example, 5 people are going this way, associated with Faculty of Engineering, and there are 3 people who are coming this way. 5 is this way, and 3 is this way. How much is on this side? 2. Because eventually, if you take a look at this, you can see 3, 5, the human being here would be 2. It's kind of opposing value. 5 of them is going this way and 3 of them is going this way. Eventually you build up 2 people on this side. You need to take care of all the stocks you have. These are the numbers you need to take care of. But obviously you are also conscious that the people who are going this way through the component are actually originated from Faculty of Engineering. And you know that those people who are going this way are actually originated from Faculty of Arts. So although the natures are different, when it comes to the component, you can see what is happening inside. Now, let's take a look at this one more time. Suppose it's in the evening, and everybody had a class on this side. Faculty of Engineering, Faculty of Art, everybody had a class on this side. And everybody wants to go on this side of the church and eventually go home. Go to the parking and pick up the cars and go home. So what is happening? 20 people of Faculty of Engineering is going this way, 18 people of Faculty of Art is going this way, 20 and 18, you can see 38 is going this way. So from human point of view, from human counts, you have 38 people on this. Obviously the reason we count this because you can't have excessive amount of people in one area. You need to take account for it and see what happens. So if they are actually going into the same direction, you count them. If they are going opposing direction, you subtract them. The same thing is true. It's like a pipe. Eventually, you can actually connect that with a pipe. Imagine you have a big pipe. The water is going this way with some pressure coming this way. And there is another water coming this way. What is the total water that goes through the pipe? In order for me to identify that, I'm going to say if this is my preferred direction, This is going to take the lead, this is going to be subtracted. That's the way I do it in the pipe. If this water is coming in and another water is coming in and everybody is actually going through the same pipe, same direction, I can see the pressure is building up, and that's the direction of the pipes and the summations of all the currents that come in. Here is the idea. Take a look at this component. That's the tunnel we talked about. This is Faculty of Engineering and this is Faculty of Art. This is one tunnel. Let's ignore, for the time being, let's ignore these voltages because I want you to just focus on the current. My preferred direction is this. When I talk about this tunnel, my preferred direction is this one. Anything that is in this direction is going to be agreeing with me. Anything that is opposing this direction is going to be disagreeing with me. So in this direction, Faculty of Art is coming in, Faculty of Engineering is opposing it. When I take a look at this, this is coming in and this is opposing it. I3 is equal to I1 minus I2. I'm going to not only assign directions, but I'm also going to assign value. Not only I'm going to say this is clockwise directions, but I'm going to say, let's call this I xy, let's call this I theta, let's call this I alpha. Let me actually make it alpha, the same thing we use inside the classroom, and let's call this I beta. I'm going to say I3 is equal to I alpha, that is in agreement, minus I beta. Take a look. I3 is equal to I alpha minus I beta. What is I3? I3 is the component current. What is I alpha? I alpha is about the entire Faculty of Engineering or Faculty of Art. So this one is going to be dedicated to the entire loop. This one is dedicated to the entire loop, but this is component current. I'm trying to transform component currents to loop currents. That's what I'm trying to do. Let's go and actually apply this understanding to all of the little i's and then come up with a strategy. Okay. When I take a look at I2, this is a specific tunnel and only Faculty of Engineering goes through it. So obviously I2 as the current of this component is the same as I beta as the current of the loop. You see this one? This is I2 and I beta is actually going the same direction, coming in the same direction. So it's going to be I2 is going to be I beta. IY is going to be I beta. Once again, you can see this one is touching this. This current is going to be exactly in the same direction as this one. If they are opposing it, I'm going to assign a minus sign. Let's go for I1. How much is I1? I1 and I alpha, they are in the same direction. So I1 is going to be I alpha. Ix and I alpha, they are in the same direction. Ix and I alpha. You can see from this structure, just by this simple look, that if I know I alpha and I beta, I would know all the currents in my design. And that's going to help me. Let me put this into this and see if we can get a mechanism in place. Let's go. I need you to keep this in mind on your notes, please. But I'm going to erase this. I'm going to replace I1 with I alpha, I3 with I alpha minus I beta, and I2 with I beta. And then come up with a strategy to write the equations. So let's see. Minus Vx plus R1. I1 is actually I alpha. R3. I3 with that direction, I alpha minus I beta as equal to 0. Let's go for R3. Minus R3. I3 once again is I alpha minus I beta plus R2. I2 is going to be exactly the same as I beta plus Vy as equal to 0. Here is the scenario. If I know I beta, I would know I2. If I know I2, I would know V2. If I know I alpha and I beta, I would know what I3 is. If I know I3, I would know what V3 is. If I know I alpha, I would know I1 and I would therefore know V1. All I need is to find the loop currents. All I need is to write these two equations, find the loop currents, and then come back and make the connections between the loop currents and the component currents and the component voltages. Let's see if we can actually look at this. You see, in order for me to write this set of equation, I went back into chapter 2. I actually wrote KCl, KV law and component laws. That was a big equation. And then I made to this stage. Can I write this without going through that part? That's what the engineer says. So I want to make this very easy to write. If you take a look at this one is loop alpha, this one is loop beta. Take a look at this. For loop alpha, I have I alpha, and it's positive. And of course, I beta is opposing it. When I take a look at this, what do I see? I see I beta, and I also see I beta positive. So the rule becomes a lot simpler. I'm going to use that rule and see if we get the same answer as you just saw from the exhaustive process. I'm going to eliminate anything that is assigned in. So I'm not going to have any polarity. If you have a polarity on this circuit, I want you to ignore this. Because when you are writing the mesh equations of KVL law, those polarities in the technique I'm about to explain don't really count. Take a look. When I want to write the KVL law for this loop, I'm going to assume I alpha is the biggest one in the design, because I don't know what's happening outside. I'm going to at least momentarily assume that I alpha is the biggest one. Because I'm the biggest one, anything that comes in with me the same direction, I'm going to add. Anything that is opposing me is going to be subtracted. This is going to act, I want you to actually consider the concept of master and a slave. This is master and this is going to be the slave. And then you go in and you follow it. So basically what happens? Take a look. Let's start from this point. This is going to go, the head of this arrow is going to see the minus sign first, minus Vx. As this is coming in, this current is coming in from left to right. You can imagine it's going to be, my imagination, it's going to be plus on this, minus on this. Because the current goes this way, Ohm law, plus minus, and the head of the arrow hits the plus side anyway. So it's going to be R1 I alpha. Then I'm going to go into R3. For R3, I said I alpha is the biggest one. And anything else is smaller than this. So I alpha is the biggest one. If you say, for the sake of numbers, very crazy number, suppose that I alpha is 100 amp, huge number, and then I beta is just 1 amp. 100 amp, 1 amp, the outcome is 99 amp. And 99 amp is actually going this way. Therefore, this is positive, this is minus, negative. And therefore, the head of the arrow is going to hit the positive sign first. As such, I'm going to say this is R3, I alpha, the master, I beta, the slave, and it's opposing. And it's going to be equal to 0. let's begin this loop. As soon as I begin a new loop, again I make a very silly assumption. This is a silly assumption. It's just meant to help me write my equations. I'm going to go into this, and I'm going to begin from this point. As the head of arrow hits the Vy, I'm going to see plus Vy. Then this arrow comes in. You see, this arrow has two messages for me. First of all, the direction. Second, the value. The value of I beta is a lot bigger than I alpha. That's a silly assumption. I beta is a lot bigger than I alpha. I beta now is 100 amp, and I alpha is 1 amp. 100 amp is going this way, 1 amp is coming this way. 100, 1. 99 amp is going this way now. Because of that, this is going to be plus, this is going to be minus. So it's going to be plus R3 times I beta minus I alpha. I beta is taking the lead, I alpha is opposing it. I beta in one sense is the master, and I alpha is the slave. And then I get to the R2 scenario, and all I see in R2 is I beta. I beta as equal to 0. I use a silly assumption or two to write this equation, but I want you to see if this is the same as this or not. Vx, R1, I alpha 1, I alpha, R3, the same. Take a look at this. You have Vy, you have R2 I beta, and you also, if you put this minus inside, you're going to get R3 I beta minus I alpha. So each time, I'm going to go into the component and see if the directions are going to be agreeing. If they are agreeing, that's the summation. If they are opposing, that's going to be a subtraction. I'm going to go in and I'm going to actually solve a number of questions before I begin the concept of Supermesh. This is, I'm just going to pick up question number 348. 348. Everything is in kilo ohm. Kilo means 1000. And inverse of that, when I want to find the currents, I remember it's going to be milliamp. That's what you usually see inside the lab environment. 2 kilo ohm. Five, 10, 1 kilo, plus minus 8, plus minus 12, and 6. I'm assuming these are ohms. Okay. Now we are in the mesh territory. What we need to do, we need to identify the loops, basic loops. We have shown before, and we talked about it, that if I write KVL law for the basic loops or primitive loops, then I'm going to actually be safe and sound. So let's go, for the sake of simplicity, I'm going to assign Ix, Iy clockwise, Iz clockwise. Please go all the way so that you don't make a mistake. I, X, Y, Z, theta. This one, try to expand as much as possible, because one thing I saw in exams is that if you don't expand this properly, for example, I saw people actually doing it like this. Okay, this is correct though, but many people when go into the 5, they don't see this. There is no I connections with this. 5 is actually interacting with 2 loops. So I would recommend strongly that you please go ahead and try to expand this so that it does cover as much component as possible. So this is going to be I theta. Okay. You have 4 loops. For each loop you are supposed to write a KVL law, except for the case where we would know what the current of that loop is. And I'm going to show that to you in a different example. Let's begin loop number X. See, I don't assign the currents or voltages to anything. I don't say this component has this current. If inside the exam or inside the lab, the direction of the current is given, the polarity of the voltage is given, you simply ignore them until the last stage. You simply write it safe and sound, and then you begin connecting that concept with the in the last step. So Ix, let's begin from this point. I'm going to hit the 12 volts from the minus polarity first. When I get to the 4K, remember when I say I'm writing equation for loop number X, I'm assuming this is the biggest current of the entire design. This is biggest and no one can compete with this. So if this is the biggest, when I get to any component, either someone is subtracting from me, just a minor subtraction, or someone is adding to my strength, just again minor addition of a strength. When I get to this component 4K, Ix is master and it's going this way. I need you to see this. Ix is moving and it's coming this way. And I theta that interacts with 4K is actually coming this way. So Ix is going this way, I theta is going this way. Let's see. It's going to be 4K, Ix is the master, I theta is the slave, and they are opposing. When I get to 1K, this is master, this is a slave, this is the biggest, this is smaller. So I'm going to say plus 1K, I don't have to write the K on top. I know that when I solve the system, my I's are going to be in milliamp. So I don't have to write it down. 1K. Which loop am I talking about? I'm talking about Ix. Which current, which loop is the neighboring loop? That's going to be Iy. The question is, are they opposing or are they adding? So in this case, Ix is coming from top to the bottom and Iy is coming from bottom to top. They are opposing each other. That's why it's going to be minus. You may be tempted to think that all the time these two currents are opposing each other. That's not going to be the case, especially when we talk about supermesh. It's going to be a different universe. So at this time, just examine if they are opposing or they are not. When I get to the 8 volt, I'm going to have plus 8 as equal to 0. So it's continued. This one is continued. Okay? That's loop number X. Let's begin loop number Y. Loop number Y is this one. This is the major loop. You have Ix, I theta, Iz. These are the neighboring loops. And each time I want to be conscious as to what is coming, what is going, opposing, adding. What's the idea? Let's begin from this node. Well, Ix is coming in, hits the minus 8 polarity first. Then it gets to 1K. Iy is obviously the leader. Ix is obviously the follower. So Iy, Ix, we are talking about 1K. Iy is going this way. Ix is actually opposing it. So it's going to be subtraction, because they are not in the same direction. Let's go to 2K. I'm talking about this component. This component is shared between this loop and this loop. Because it's shared, I need to have two currents. Iy is the leader. I theta is the follower. Are they in agreement or disagreement? Iy is going from left to right. I theta is going from right to left. So it's going to be minus. And then I'm going to have the 10. This 10K is shared between these two loops. Iy is obviously still the leader. Iz is the follower, and I need to know how they interact. Iy is coming from top to the bottom, and Iz is going this way. So it's going to be Iy minus Iz as equal to 0. I covered all the components. 1, 2, 3, 4. 1, 2, 3, 4. I want to do the other two for the sake of this experiment, and then I want to give you some additional information on a different type of a circuit. Let's go for loop Z, this loop. I want to start from this end. The head of the arrow hits -6. Then it comes in. Iz 10K, Iz is the leader. I1 is the follower. This one is coming this way. This one is opposing it. Then I have 5K. This is shared between these two loops. So I have Iz from the primary loop and I theta from the neighboring loop. And I can see this one is going this way and this one is actually opposing it. Minus as equal to 0. Finally, let's write the equation for loop theta. Loop theta, 3K, 5K, 2K, 4K. I have 4 terms. I need to write 4 components. I need to write 4 terms. Let's begin from this point. 3K sees only theta, so 3I theta. It's always plus, except if it is forced upon me, it's always plus. So let's go for 5K. I theta is going this way. Iz from neighboring is going to oppose. I theta is the master. Iz is the slave. Then I go for 2. I theta is this, and Iy is opposing it. I theta minus Iy. Then I'm going to have the 4K, and it's going to be I theta minus Ix. I'm continuing this because I don't have a space, is equal to 0. This 4 terms is going to be the equation for theta. Okay, I'm going to go in and basically trigger a different type of approach, different type of understanding of this design. Any questions so far? Okay. Suppose you have the following design in mind. This is 2 amp. This is 10, 5, 20, and then a resistor and a power supply. So far in the examples I reviewed with you, I did not include a current source. Now you can see there is a current source in this structure. Okay. As long as we have understood what we attempted to do, we should be just fine to write the equations. If you want to solve this using chapter 3 nodal, you have 1 as a reference node, 1 and 2, two equations to unknown. But I want to solve this. The question is asking me to solve this using mesh. I have 3 basic loops. So I'm going to have this as Ix, this as Iy, this as Iz. When I want to write this loop, I am facing a component that is dictating to me how much this current is going to be. This is the component current, and it is 2 amp. This loop is interacting with this component and only with this. This one and this loop, they are only one-on-one. There is nothing else. Because of that, I can safely say Ix is equal to 2 amp. This is a 2 amp component current. Remember when we had this one, when we had I5, we said I1 and I5 are the same and therefore they are equal in the last examination of the design. In this case, the current seems to be interacting with this loop and therefore Ix and 2 amp would be exactly the same. What is the purpose of writing the mesh equations? The purpose of writing the mesh equation is to find the currents of the loops. You already have the current of the loop. Therefore, unless it is absolutely necessary, we do not write KVL law for this. It's already done. It's already known. If you plan to write KVL law, then much the same way as the nodal scenario, you need to give me a voltage for this component because this is KVL law. The mistake I see inside the exam is this. The mistake, they say 2 plus 10 times Ix minus Iy as equal to 0. This is very wrong. Fundamental mistake. That's going to actually, we are going to scrap your 10 marks or whatever it is associated with this because this is amp. This is volt. You can't add apple and orange and then say it's equal to 0. This 2 is just a 2 amp. You need to say, if you want to write the KVL law for this, you need to say plus Vx plus 10 Ix the master, Iy the slave, and then you are safe. But why do you want to introduce Vx if you don't want to? If you don't want to know this, you don't have to do. If you want to write it, yes you can. Do you have to write it? No. That's why we recommend at this stage to please, when the current of the loop is known, try and avoid as much as possible writing the KVL for that loop. So let's see. This current source is touching the loop current once, and that's why it gives me confidence to say Ix is equal to 2. I'm going to give you a different scenario in a moment. Let's go into this one. Loop number Y. Loop label Y. So I'm going to start from this point. It's going to be 10 times. Iy is the leader. Ix is the follower. This is going this, and this is opposing it. It's minus. This I have 5, and only Iy is going through this. Then I have 20, and I can see Iy is going this 20. Iy is the biggest, and Iz is the small one. Iy takes the lead. Iz is a slave. So Iy minus Iz as equal to 0. That's the equation for loop number 2, or label Y. Loop label Z. Let's begin from this. The arrow hits the 8 volts. I have no choice but to note on that. Then I'm going to have 20. It's going to be Iz is the leader. Iy is the slave. And in this case, Iz is going this way, Iy is opposing it. That's going to be the case. And then of course the 2 ohm. Remember, you have 1, 2, 3 components. You need to give me 3 terms. 2 times Iz as equal to 0. Obviously, you could replace Ix with 2 amp because you already know that. Is there any Ix? So this is going to be two equations, two unknown. What did we do so far? We said that as a result of a different perspective on the equations we got from chapter 2, we can rearrange the equations, collapse the system into mesh equations only. In order to write the mesh equations, we ignore all the polarities and confusing directions of the currents. We only safely and soundly assign the currents to the loops. For my sake, please assign clockwise, because it's a lot easier for us to do grading. Clockwise, and then if they are anything, they are coming into the component, they are in the same direction, you add them. If they are opposing, you subtract them. In this example, we said, if you have a current source that is touched by the loop current only once, then you can safely say Ix is equal to 2. Now I'm going to begin the concept of the supermesh. Let's see what the supermesh, the challenge is. First, identify the challenge. I'm going to identify it. I'm going to say how we need to see this so that we can safely write the equation for it. Let's assume you have this parallel structure in your mind. This is R1, this is R2, and this is Ix. If you were to write the necessary equation for this, you would say this is one loop, I1, this is two loops, I2. Because this current source is touched by I1 once, you can say I1 is equal to Ix and say, yes, I'm done. And then go into loop number 2 and start from this end, for example. It's going to be R1 times I2 minus I1 plus R2 as equal to 0. It is then the concept of one equation, one unknown, because I1 is already known, I2 is the only unknown that you can find from this equation. R1, I2 takes the lead, R2, I2, my mistake, thank you, as equal to 0. If I were to make that mistake inside the exam, that would be a fundamental mistake. So this is going to be R1, I2 minus I1, I2 takes the lead, I1 is following it, and they are opposing each other, and then I have R2, I2 as equal to 0. Since I know I1, I'm going to have this as one equation, one unknown. But you see, this structure is constructed of three components in parallel. You remember when we talked about parallel structures, we said that parallel structures enjoy a number of simple properties. The voltages are going to be the same. The way they are connected head to head and toe to toe. If I have a partner, the partner is standing in front of me. I'm looking at his or her eyes, head to head, toe to toe. We are in parallel. Now I want you to imagine that I actually moved around and my partner is here now. We just changed our positions. Now I'm going to see my partner, his or her eyes, just as the same way as I did before. And our feet are going to meet, head to head, toe to toe. Right? So in that sense, because these two components are in parallel, you can actually replace them. You can actually switch them over. You can grab these two resistors like the same time last time. Grab them out. Because this is a rubber band in my silly mind. I'm going to take this out and I'm going to actually change their position. Any two components in parallel, I can actually change their positions. As such, I want you to take these two now and I want you to change the positions. I want you to imagine the following design. This is R1, this is Ix, This is R2. Am I supposed to get any different? No. This structure is exactly the same as this structure. The voltages are the same. Whatever the currents are, I'm going to find it. Really, there is nothing different. If this voltage is the same as this voltage, the current is the same. If this voltage is the same as this voltage, the current is the same. If they are supposed to have unique voltages, they are going to have unique voltages. These two structures are exactly the same. But let's see what the kind of a challenge I'm going to see when I want to solve this using mesh. Okay. This one. This one. I'm going to call this I alpha. I'm going to call this I beta. How do you say Ix is? In order for you to write the KVL law, you have two options. One option is to utilize the understanding we just did, but by introduction of a new variable. The other topic would be to do the supermesh. You see, if I wanted to write KVL law for this loop, what can I say? I'm going to say start from this end. Well, let's start happy node. And then I come in, what do I see? Plus minus? Minus plus? I don't know. Because that's a current source. And a current source can have any voltage across. So in order for me to have a successful assignment, I need to actually assign a new variable, Vx, across this. Then I can say R1 I alpha plus Vx as equal to 0. That's one thing. Then when I go into this loop, let's start from this end, minus Vx plus R2 I beta as equal to 0. Sure. What happened to your current source? Current source which is well known to you, and its value is Ix, which is 10 amp, for example. What happened to that? Then we are going to say Ix, which is going this way. Who is agreeing with me? I beta. Who is opposing me? I alpha. You are going to say Ix is going to be I beta minus I alpha. You have, instead of one equation, one unknown, you have three equations to your known. And that's a bit of a burden on us, especially when the size of the circuit grows. This is going to be a huge headache for us. The textbook has gone through this technique. Plus minus. It's a correct approach, but it's excessive sometimes. And you can take a look at it if you like, but you can also listen to me, and that's going to be, I'm going to get you the one equation, one unknown. The way I'm going to do it, you have to listen to me, okay? So this technique is fine. I'm going to erase this. I'm going to erase this new variable that has caused so much pain in my process. I'm going to identify the design. Well, I have R1, R2, Ix. I'm going to identify the basic loops, alpha and beta. So far, we are in common. But I want to ask you this question. Where is my current source? My current source is between the two loops. This current source is now shared between loop alpha and beta. This current source is communicating with this and this. If you go back to chapter 1, we said that you happen to have so many different loops. In this case, you have one loop here, one loop there, and of course you have a bigger loop that is not a basic loop. Now we are going to utilize those additional loops we never touched before, because it's going to be making us very happy in terms of number of equations. As soon as you see something like this, you are going to go in and say, I want to make sure that the current source is only touched once. So this is a current source, and this current is coming in, touching it, whether opposing or agreeing with it, that's a different issue. But I want one of these guys to talk to this, not both of them. I'm going to go in and remove one of these guys. You removed a basic loop. You have to replace another loop. If you have 10 basic loops, you need to give me 10 equations, no matter what you do. So if I remove this basic loop, you need to give me another one. Because I removed this, I am in deficiency in terms of number of necessary equations. And specifically in this specific design, R1 hasn't been touched yet. Of course, there could be a scenario when R1 is also touched. So that's a misleading part. If you see that all the components are touched, don't say I'm done. No. If you have 10 basic loops, you need to give me 10 equations. If you have 5 basic loops, you need to show me 5 loops. When you get rid of one, you have to replace it. So I'm going to remove this. But the only thing that is left for me would be this big one. I'm going to call this I theta. Of course, this value is going to also change, but I don't want to put prime on it. Let's see what happened. I'm going to remove this. Let's see this. What do you see? This current source now is communicating with loop beta, and therefore I know what I beta is. I beta is equal to Ix, which is known, 10 amp. They are in the same direction, and therefore I'm going to say it's plus. If they were in the opposite direction, they would be minus. I just found I beta. I have one more equation to write, and that would be the big loop. Let's begin from one end, this end. You have R1, and R1 only sees I theta. I theta is the master, everything else is a slave. I theta is the leader, everything else is actually following. So I theta, R1 I theta, plus I continue my trip, I get to R2. This is going to be R2, but when I see R2, I see two currents that are going inside. I beta, I theta. They are both from top to the bottom. They are in the same direction. Therefore, this is going to be I beta plus I theta as equal to 0. I already know this. This is Ix. You have one equation, one unknown. So which option would you choose? That's your choice. You can choose extra unknown, 2 extra equations, or you can actually leave a lot simpler by looking at this. This is what we call in this class supermesh. Supermesh has been defined by textbook and other textbooks differently, but please help us conduct this consistently. I want to go in and solve a number of supermesh. Okay, let me begin and pick up some currents. Let's say 318. Okay. That's going to be 10 volts. This one is not working, so I'm going to see which one is good. 2 ohm, 2 ohm, 5 amp, 4 ohm, and finally 8 ohm. I hope I have everything. Let me solve 2 questions with the concept of supermesh. Okay. Supermesh is a subset of mesh. Mesh is all about KVL law. Although I'm utilizing the current of the loops, I'm writing voltage plus voltage plus voltage as equal to 0. All the elements are going to be volts, so I need to be conscious about that. how many basic loops do you have? You have 3 basic loops. 1, 2, and 3. Question, do you have a current source? Yes. Are you touching that current source twice or more? Yes. This current source is touched twice by these 2 loops. You need to remove 1 basic loop and replace it with a new one. So in this case, for example, I want to remove this one for the sake of variety. So I'm going to say you need to remove this. But obviously you need to encompass a different loop where at least this 8 ohm has been touched at least once. So in this case I have this loop in mind. That's one possibility, right? What else do I have? I don't have any other possibility. You can also do the last one, the outer one. Let's do that. I'm going to remove this. And I'm going to go and basically make it a bit difficult, so let's go this way. Let's label them now. IX. IY is this one, so let me say this is IY. And this is going to be IZ. Okay? Okay? Okay. So the question is, how much is IY? Do I have a current source cleared now? Yes. The current source is now touching this loop current. It's only touching it once. There is nothing else that shares this one. I removed 1 basic loop, but then I replace it with another loop. If you have 3 basic loops, you need to give me 3 equations no matter what. So I removed that. Loop I, labeled Y, IY. I can see IY is coming from top to the bottom, and I can see the current source is going from bottom to the top. So these are actually opposing each other because the current source is seeing this only once. I would say IY is equal to -5 amp. I'm done. Of course you can write KVL, but in order to write the KVL for this, you need to introduce the voltage across the current source. Otherwise, that's not valid to do anything else. Loop Y is done. Let's go for loop Z. For loop Z, let's begin from this end. That's simpler. I see 8 ohm. I see IZ and I don't see anything else. Then I continue my trip. I come in and I see 4 ohm. I come in and I see 4 ohm. And in that 4 ohm, I see 2 loop currents. One of them is coming down. IZ is the master coming up. IY is the slave coming up. Both of them are actually coming up. They are the same direction. IZ is the master. IY is the slave. But they are in the same direction. Let's continue my journey through 2 ohm. That's another challenge you need to see. In 2 ohm, I don't see just 2, I see 3 loop currents. IZ is coming. IY is coming in the same direction, but IX is opposing it. So let's begin. Actually, I want to write that down so that I have all the components. So it's +2 times. IZ is the master. IY is the slave. IX is the slave. So I know I need to identify these components, these currents. I have 3 currents that go through this 2 ohm. This one. But I can see IZ and IY are in the same direction, and the outcome is opposing with IX. Plus, let's go to the next and final 2 ohm, this 2 ohm. Obviously, IZ is still the master, remains the master for the entire equation, and I have IX, but I need to see if they are opposing or not. In this case, IZ is going this way, IX is going this way, so it's going to be IZ minus IX as equal to 0. I'm done with loop Z, which was a big and more challenging loop to do. Let's go for loop X. For loop X, I have 3 components. I need to be very careful on this. Let's begin from here. I'm going to see -10. I can't do anything else because the head of the arrow comes in and hits the minus polarity first. Then I'm going to go and see this 2 ohm. Now I'm writing the equation for loop X. Therefore, X is the master. What else going into the 2 ohm? Z is the slave. Are they opposing or are they agreeing? This is X, this is Z. Therefore, they are opposing. Let's begin. I want to write it down on this side. This is the last 2 ohm, these 2 ohm. I did this one, I did this one, I need to do the 2 ohm. For this 2 ohm, Ix is the master. Obviously, this 2 ohm is interacting with Iy and Iz. So it's going to be Iy and Iz. So it's going to be, if you take a look, Ix is going this way. So far so good. You see, you can follow my pen marker. Iz is actually going this way, opposing. Iy is actually coming in opposing. Therefore, both of them are actually opposing Ix is equal to 0. That's how we write the equation for the supermesh. I want to do one more supermesh and then close this topic of the chapter 3. The next stage for this is to actually replace Iy with -5, and please remember to put -5 in a bracket. So that's the next thing I'm going to do. It's going to end up having 2 equations, 2 unknown. And the next thing I'm going to have, I'm going to organize this, simplify this. I'm asking you to have all the Iz on one end, all the Ix on the other end. The same thing for this, all the Iz, Ix. The sequence has to be the same. Iz, Ix equal to some constant values. That's the way we create the system. And then you utilize the calculator. It's very important to write the equation safely. It's important next to actually simplify it, and then obviously utilize your calculator to get it done. Okay, I want to do one more. Okay. This time I want to do 338 amp, 3 amp, 3 ohm, 1 ohm, 2 ohm, 1 ohm, 2 amp, I'm sorry, 2, yeah, and then 4 ohm, and then 9 volts. I hope I have everybody in the design. Yes, I do. Well, obviously I have many chances. In chapter 2 I would be writing perhaps 20 equations to unknown, I'm just guessing. In Nodal you have to identify the nodes, you have to pick up your reference node and do the job. If you pick up this as your reference node, that would be a super node. If you pick up this as your reference node, this would be your super node. So still you are facing some challenges. Then here we would like to do is in the sense of mesh and supermesh. Supermesh is a subset of mesh. I need to identify my basic loops. Basic loops are the loops that they don't have any loops inside. These are basic. You don't see anything inside, do you? No. So these are my basic loops. I'm going to sacrifice one of the basic loops for the benefit of a smaller, faster writing of the equations. If I take a look at this, I can see it is interacting with the loop current and only one. This is safe. If I take a look at this though, I can see two loops are touching this. A current source has to be touched only once in the technique I'm talking about. Not that it's not possible, but in this technique, a current source is supposed to be touched only once. So I need to get rid of one of the loops, basic loops, sacrifice it, and then I have to replace it though with a different loop. I need to remove, for example, some of either this or that, doesn't matter. And then you need to pick up something else. You can pick up this big one. You can pick up this big one, the L shape. But can you pick up the big one outer limit? No, because you are going to touch this more. You can go outer limit because you have to be conscious. So let's do this. Let's make it simpler for both of us. I'm going to actually pick up this one. And I'm going to start labeling them. Now this is IX, this is IY, this is IZ, and this is I theta. You might feel a bit funny on the theta loop. You see a 1 ohm in series with 2 amp. 2 amp is a force you need to live with. There's nothing you can do with this 2 amp. This 2 amp says that this branch is mine. The current of this branch is 2 amp. So whether this 1 amp ohm exists or not, really doesn't matter. You can actually replace this branch only with a current source of 2 amp. This 1 ohm can be shortened in that sense. But I don't want to do that. Let's leave it at this. Because someone has an interest in that. So let's leave it at that. This current and this loop current are actually communicating once. So therefore, I theta is equal to, now, I theta is going this way. The 2 amp is going this way. They are opposing each other. I'm done. One loop is done. As soon as you know the loop current, try to avoid writing KVL law for it. If you want to write KVL law for this, you have to introduce a voltage across the current source. Then write the new KVL. So please be careful on that one. Because I'm done, this loop is done. Let's take a look at IZ. IZ has a 2 ohm on top, 9 volts, 4 ohm, 1 ohm. Let's start from here. It comes in, the head of the arrow hits the minus, the plus polarity of the 9 volts. Then it gets to 4 ohm. 4 ohm, and you see IZ going in. And only IZ is going in. Then I'm going to see 1 ohm. IZ is the master. I theta is the slave. Are they opposing or agreeing with each other? This is IZ going up. This is I theta coming down. Therefore, they are opposing each other. Plus, I need to take care of this 2 ohm. 1, 2, 3, 4 components. 1, 2, 3, 4 terms. 2 ohm. Don't forget that. Your equations are supposed to be complete in that sense. So 2 ohm. What do I see? What is going inside? IZ is going in. Also, I see IY and IX are communicating. I'm going to write them down. The question, are they cooperating or are they opposing? Now, IZ is going from left to right. IY, right to left. IX, right to left. So IZ and IY and IX are actually opposing each other. Let's take a look at my IY. Well, one of the things we did, and interestingly, we did it to simplify, is this. This IY is talking to 4 amp, and 4 amp is only talking to IY. There is nothing else that talks to 4 amp. And therefore, IY is equal to 4 amp. Are they in the same direction? Going up, up. Component current, loop current. They are the same. This loop is done. Okay, let's do the big loop, this one, loop X. So let me draw a line. That's the last loop, and we need to be careful. Take a look at this loop. I know everybody is tired, but you need to know exactly the number of components. 1, 2, 3, 4, 5, 6. I need to have 6 terms. Because I don't have a space, I'm going to erase this. I'm going to actually write it down on top. It's going to be I theta is equal to, it was minus 2m. So I write it down. So I want to write the big one. I start from here. The head of the arrow hits the minus polarity first. Then it continues. 4 and Ix are the only thing that they communicate and mix up. Nothing else. When I get to the trio, I see Ix and I see Iy. Ix is the leader. Iy is the follower. Ix is going from left to right. Iy is also going from left to right. Therefore, you add them. When I get to 1 ohm, Ix is the master. Iy is the slave. Nothing else is involved with 1 ohm. So Ix is coming from top to the bottom. Iy is coming from top to the bottom. Take a look. And therefore, they are actually adding each other out. In one sense, this makes sense because you can say 3 and 1 ohm are actually in series. You can combine them and have a 4 ohm. That's what exactly this equation is telling you about. So let's take a look at the 2 ohm plus 2. I'm going to continue the 2 ohm here. 2 ohm is challenging. Ix is the main component. Iy and Iz are also talking to this. So it's going to be Iy and Iz. Who is opposing? Who is agreeing? Ix is coming from right to left. Iy is coming from right to left. Iz, though, is coming from left to right. That's the way we do it. And then the last one is going to be the 2. These 2, Ix is the master, I theta is the slave. I can see from the graph that Ix and I theta are opposing each other. So it's going to be Ix minus I theta as equal to 0. The next thing you can do is to replace I theta and Iy, and the system collapses into 2 equations, 2 unknown, and obviously that's an easy thing to do. As you can see, this is relatively challenging, but if you wanted to do the original mapping, which would be basic, the number of equations are going to be a lot more than 2 by 2, perhaps 6 by 6. So it's a matter of exercise, making the right decision. In this class, please, when you see a question in front of you, don't jump to the solution. Just sit for a few seconds, make a plan, game plan, as to how you want to solve this. Is it a supermesh, supernode? Which one is going to be involved? And if you make that decisions, that few seconds right, then you are going to be just fine in terms of writing the fundamental equations, which is going to take you a long way in terms of grades, and then obviously simplifications, and then the answer to the final answer to the equations. By this, we have finished chapter 3, and we would be starting chapter 4 next. Thank you very much.